Good day everyone, I am Frederick Salimi, Director of PMC Overall. This e-course will be uploaded in a training workspace of EPC 365. If you have any questions, please send us an email given in description. Have a good day and talk to you later. Today we discuss about layout principle to prevent hazardous occurrence. We discuss about fire zone, ESD location, restricted area, impacted area, and safety distance calculation. This is a generic version and will be customized later. This training course takes 1 day. We give you access 1 year to EPC 365 training monitor for discussion. You will get a certificate of skill after achieving a score of 80/100. The target trainee are plant managers, operation managers, project engineers, technical authority, engineer managers, lead engineers, HSE design engineers, and process safety engineers. This course gives a practical understanding of the fire zone, ESD location, restricted area, impacted area, and safety distance calculations for oil and gas installation. A brief description about myself. I have a master's degree in dependability, which covers safety, reliability, maintainability, and availability. I have also a BS degree in process control and instrumentation. And also certification of their accident investigation from root causes in Houston and QRA in UK. I worked several years as lead safety engineers in Technip and Worley Parsons and AMEC in engineering companies, and I worked several years in operators like Total and Ajib for Kashagan project. I've been involved in several different phases of the project, from pre-FEED, FEED, detailed design, construction, and operation. Fire zones are the areas within the installation where equipment is grouped by homogeneous level of risk. Now I show you here how this is an installation and how fire zone are defined in this installation based on calculations. This is fire zone 1. Fire zone 1 means that means if there is a fire and explosion in this area, which is receiving facility, slug catcher, LP separator, mercury removal unit. If there is a fire and explosion, it will not escalate to the adjacent here to fire zone 2A or fire zone 2E. Here, fire zone 2A, we call them fire zone 2A, and this one fire zone 2B, and this is 2C. Why are there fire zone 2 and here 2E? Because if there is a fire happening here, which is compression area, because of the safety distances, it will escalate to the hydration unit next to it. And the same thing, if there is something happening in the hydration unit, it will escalate to this dew painting or compression area. So that's why we call them a fire zone 2. So what is the fire zone? And this in fire zone, normally when there is a fire explosion, we isolate this and then depressurize it, this area. It can be pressurized, this one. And the same thing for this area. If there is a fire and explosion, we can isolate this. The EST valve will be closed, and we depressurize this area. But this one can be pressurized. Here are the other fire zones. For example, fire zone 8 is they are some electrical generator, and the fire zone FZ3 is full gas uh, installation. So then basically, if there is fire zone, if something happening here, it will not escalate to this one. So the concept of fire zone is, by calculation, we regroup all the equipments in such a way that if there is something happening here, it will not escalate here. For the deluge system, the same things. It is for calculations of the fire water demand. If deluge system here is initiated here, we don't initiate the deluge system in this area. So that is also helping to optimize the capacity of the fire water pump. EST location, normally we have to define EST location where they are, because they are very important, and they have to isolate the fire area. For example, between this and this area, there should be an ESTV somewhere, and here in safe area, that if there is a fire here, or and this EST, it will be in safe area, it will do this function and works for that. If EST it comes in the fire zone, it has to be passively protected against fire and explosion, and it has to be written in performance standards for EST valve, because isolation valve, they are safety critical element, and we have to have it in the performance standard. But here, because there are one fire zone 2AB, there is no need to put a EST valve between these areas. Restricted area, normally restricted area is for definitions of the fence. For example, this is area. If the restricted area goes up to here, we have to put a fence in the installation, and that means that the company is the people who are working in this area, they accept the risk, and they are inside the boundary for the property of the company. Impacted area is those areas after the fence, and for example here outside the fence, and any if there is impacted area in this area, people, the public cannot build a building, etc., because there might be if there is a releases here, and there must be some toxicity for the people, so they are not allowed to build a building in the impacted area. So now application scenario outcome. So we have to simulate different scenarios. Here, if you see for fire zone, restricted area, and impacted area, for all of them, we have to simulate jet fire, pool fire, vapor cloud explosion, which we define the overpressure. Belly V is for restricted and impacted area, and etc. These are, for example, pool evaporation for fire zone for LPG. So we will discuss about it later. So you have to know that which scenario we take for calculations of the fire zones. So the fire zones, we have to look at the flammability, and this is for LFL. For thermal radiation is 9.5, and normally we use a 20 millimeter release. This is 20 millimeter release is basically is a credible scenario, because most of the flanges, etc., they are between 7 millimeter release. But if in the worst case we have 20 millimeter release for drop object or some accident, and that is the criteria for calculations of the safety distance for fire zone. And the initial release rate for 10 minutes. So all of these things criteria is written here. The same thing for restricted area flammability LFL, and toxic gas is LCL 1%, and for the restricted area, for the thermal radiation is 4.7, and for the flare, and if you want to for continuous operation is 3.2, and etc. For Bellevue is kilowatt per square meter, etc. These are again for the restricted area. We have to, for overpressure is 140 millibar. We have to look at that one. And then one thing that I have to say that release of the restricted area is 20% of the larger diameter in the area, diameter of pipe. So here 20% pipe diameter limited to a maximum size of 20 millimeter. So, and a leak size of 150 millimeter. This is for impacted area. And for the toxic gas, we have to, the criteria is immediate danger to life and health, IDLH. And for thermal radiation for jet fire is 3.2 kilowatt per square meter, and for in case of the liquid release and in case of the flare is 2 kilowatt per square meter, and for Bellevue is 600 kilowatt per square meter. So impacted area is criteria for the overpressure 50 millibar, and for toxic gas is IDLH, and we have to calculate this, and we have to remember that if we do the 2 kilowatt per square meter, it is including solar radiation. So as a summary, for fire zone restricted and impacted, the criteria for all of this is given here. So LFL for both restricted area and for fire zone, and the normally for the thermal radiation 9.5 kilowatt for fire zone, 4.7 for restricted area, and 3.2 for impacted area. 200 millibar is for the fire zone, 140 and 50 millibar for impacted area. Of course, when you go for 50 millimeter, it goes very far. I added the Explo CFD, which is presented by Dr. Adel Jawad. And I think this is the best package for doing the dispersion calculation and explosion for the fire zone and safety distances. The reason is because we want something quick at the beginning of the project to define and to freeze the layout of the installation. I put a CSP video, and this video is very interesting, that it is for the explosion in BP refinery, and 15 workers were killed and injured 180, and this was because of non-respect of safety distance between the people who were doing the construction and just next to the source of danger. So if you have any questions, please send us an email to pmc@epc365.com. There is also a French website and an English website, and for all of them, both of them, they have a request form. You can send an email, and we get back to you as soon as possible.
Hello, and welcome to an overview of Explo CFD. Version 7. This is the latest version released in 2020 amid the COVID-19 crisis. We're going to go through just basically how the software operates, so as to give you an overview of how things work. And it's still basically the same mode of operation. The way that the software works is basically you read in a PDF of a plot plan or an offshore platform or an FPSO, what have you. Usually it's a top view, but it can be a side view, and sometimes those are very useful. You can select the domain to be either the entire plot plan or part of it by controlling things. And then when you're ready to go, you can set it to run. And the way that it runs basically is it's a hybrid code. So the code will first analytically estimate the source terms. So if you're doing a gas explosion, it uses CSC, the confinement-specific correlation, which has been proven to be far more accurate than the multi-energy method, because it's able to decouple confinement from congestion. It also does BLEVEs. It uses the method by Prue from 1991. Basically, he's converting that into a TNT equivalent explosion. You could do a TNT equivalent explosion if you're doing something like ammonium nitrate or an improvised explosive device like a terrorist activity. Once you calculate the source, the strength of the explosion, that is then passed on to SU2 or open source CFD software, and that allows you to propagate the explosion into the wider domain, and we'll show you exactly how that works for several examples. It's run in a 2D fashion. This is deliberate because SU2 runs in a 3D way, so you can configure SU2 to run on detailed 3D geometries. There's no need for that, and in fact CFD softwares have traditionally been for explosions. All of the CFD softwares have been traditionally dissipative, and so to not be on the underconservative side, SU2 is configured in a 2D simulation. So you're basically solving at the ground level, and then the output is visualized with PowerView, very powerful visualizing tool that shows you exactly how your explosion is interacting with the rest of the domain. Let's talk about gas explosions. In the past, to do a gas explosion using CFD, you basically had to model the site in 3 dimensions. That's expensive, it's time-consuming, it may not always be possible, and in fact, the end result of 3D CFD used for explosions has a large uncertainty, and this is something that we don't discuss too often, but there's a 30-50%, even order of magnitude sometimes, uncertainty for the state-of-the-art CFD. So it pays to be conservative and to try and stay within the sort of limits or the uncertainties of 3D CFD. And that's the approach that we've taken to actually model this. So instead of doing all of that, software now relies on just the plot plan and simplifies things and stays within the uncertainty. We'll get to that in a minute. But if you were to, as bad as CFD is in terms of uncertainty, apart from CSC, the multi-energy method, for example, is even worse. And in fact, we have a paper from 2010, I believe it might be 2014, where we looked at a comparison of the gain correlation that's guideline for the application of the multi-energy method, and that's used in softwares like FAST, and we compared that to CFD. And had there been a correlation between 2 methods, then all of these points would be sitting on the line. Obviously, they're not. The R squared for the 2, or R squared between the 2, was 0.3. By comparison, one of the PhD students out of UWA actually came up with a much better method. Again, it's an analytical estimate, but this is how it compares to CFD. And it's been compared over about 3,000 to 2 sets of 1,500 cases. And you can see here the R squared here was about 84%. So this method is what is used for gas explosions as the source. just load a drawing. This is a normal plot plan of an area. You could see it's picked up all the lines, and you could select and deselect the lines. So in this particular case, we have an explosion on an FPSO off the coast of this is in Brazil, actually, off the coast of Brazil, the south of Brazil, and you've obviously got some industrial facilities here, some important sort of storage tanks here. More importantly, here, a kilometer away, there is a sort of residential area, and so it's easy to select and deselect walls or lines to be treated as walls. So, for example, this line here demarcates the shoreline. You don't want that to be treated like a wall, so you could see you can easily deselect it, and it goes purple or gray in the software. And you set up the parameters, which is very easy to do for the gas explosion or the BLEVE or the TNT explosion. You set up the gas cloud, and when it's done, it outputs the shock wave, the explosion that's coming out from the vessel. Other examples we have here. This is a redo of Bunsfield. You could see the explosion on 3 Cherry Trees Lane coming out towards the buildings. And one thing that you notice about this is you could see the reflected shock wave. If you look over here, you don't see this in normal or in other CFD softwares. You can see the reflected shock wave very clearly. Again, look over here. When the shock wave reaches the tank, you'll see the reflected pressure on the tank very clearly. And this is because we don't turn it into a porous medium or anything like that. You see that shock wave reflecting off the tank, very clear. So there's a high resolution capture. This is an ammonium nitrate explosion that's occurring on a site, and you could see it interacting with the walls, with the facilities as the explosion propagates. Obviously, the pressures are extremely high in the case of an ammonium nitrate explosion. All these are prior real cases for clients. This is a BLEVE in an industrial facility. This is a tank undergoing a BLEVE. I think, to my knowledge, Explo CFD is the only software in the world that actually models an ignition of a flashed flammable vapor on top of the BLEVE. So the BLEVE is actually the rupture of the tank, and there's a flash and an overpressure that's created. But on top of that, the released chemical may be ignited, and Explo CFD is the only software that actually models that as well. It could make a very big difference in terms of overpressure. You could go from half a bar to 10 bar if the tank were in a congested area and releasing a high energy material. We've done a lot of validation on this. As I said, the components are heavily tested. CSC and the other analytical methods have been heavily tested. And also, we've been looking at the integration of all of these components together. So these are the BFET's repeatability tests, and you can see agreement here as the shock wave propagates outwards from the source of the explosion outwards. This is about as good agreement as you're going to get from any explosion modeling software, 2D, 3D, or any other type. The software performs as well as you might expect, and of course we continue to keep testing it and pushing its limits and seeing how far, where you can and where you can't use it. But it's very easy to use, and it's a quick, rapid solution, and that's one of the more attractive features that it has. It certainly beats the sort of concentric circles that you get with other analytical methods, where the walls, the obstacles, the other features of the geometry are not taken into effect, or some method that just interprets CFD results, or interpolates, CFD results, that's you don't know where you're sitting as far as that the accuracy of that is concerned. This is a method that interacts with changing problems, so you can adapt it to cases, geometries that you have never seen before, and that is a very important feature.
Unfolding in the ISOM unit. As flammable hydrocarbons overfilled the blowdown drum, operators nearby saw a geyser of liquid and vapor erupt from the top of the stack. The equivalent of nearly a tanker truck full of hot gasoline fell to the ground and began forming a huge flammable vapor cloud. The vapor cloud expanded in just 90 seconds, engulfing the unit and the nearby trailers full of workers. About 25 feet from the base of the blowdown drum, 2 workers were parked in a pickup truck with the engine idling. As flammable vapor entered the air intake, the diesel engine began to race. The 2 workers fled, unable to shut off the engine. Moments later, witnesses saw the truck backfire and ignite the vapor cloud. Powerful explosions swept through the area. The blast pressure wave accelerated through the ISOM unit, causing heavy destruction and igniting fires. The workers inside the trailers were right in the path of the explosions. The fires continued to burn for hours. 12 of the 20 occupants of the double-wide trailer were killed, along with 3 workers in a trailer nearby. 180 workers were injured, many with serious burns, fractures, or other traumatic injuries. The wood and metal frame trailers were blown apart by the blasts. Firefighters struggled to rescue the injured and recover the victims. 50 large chemical storage tanks were damaged, and the ISOM unit remained shut down for more than 2 years. The disaster at BP Texas City was the most serious refinery accident ever investigated by the CSB.